Bubble sort is like repeatedly passing a bubble-wrapped ball through a line of objects, letting the heaviest object rise to the top each pass. The algorithm compares each adjacent pair of elements in the array and swaps them if they are out of order. After the first full pass, the largest element is guaranteed to be at the last index. The process is then repeated for the remaining unsorted prefix. Algorithmic steps pseudocode. Function bubble sort open parenthesis, a 0 to n-1 close parenthesis. For I from 0 to n-2, I equals number of completed passes. For j from 0 to n-2 minus I, last I elements are already sorted. If a sub j is greater than a sub j plus 1, swap a sub j and a sub j plus 1. Each inner loop bubbles the current largest value toward the right side. The idea is simple, requires only adjacent swaps, and works for any comparable data type. Explanation: the running time of bubble sort depends on how many comparisons and swaps are performed. Number of comparisons. The inner loop runs n-1 minus I times for each I from 0 to n-2. Total comparison C of n equals the sum over I equals 0 to n-2 of n-1 minus I, which equals n-1 plus n-2 plus 1, which equals n times n-1 divided by 2. This sum is independent of the input order, so the average and worst case number of comparisons are both n times n-1 divided by 2, which is theta of n squared. The swabs. Worst case, the array is in descending order. Every comparison triggers a swap, so swaps equal C of n, which is n times n-1 divided by 2. Best case, the array is already sorted. With the basic version no early exit flag, we still do the same number of comparisons, but no swaps are needed, so swaps equal 0. Time complexity. Best case without early exit. Theta n squared comparisons, 0 swaps, which is theta n squared overall. Best case with early exit, C optimization. Only one pass is needed, that is n-1 comparisons, which is theta n. Average case, theta n squared comparisons and about half that many swaps, which is theta n squared. Worst case, theta n squared comparisons and swaps, which is theta n squared. Mathematically, the dominant term n squared divided by 2 shows the algorithm grows quadratically with input size n. Even though plain bubble sort is simple, 2 practical tweaks make it much faster on nearly sorted data. Early exit flag sorted check. Introduce a Boolean variable swapped that is set to true whenever a swap occurs during a pass. After the inner loop finishes, if swapped remains false, the array is already sorted and the algorithm can terminate early. This reduces the best case complexity from theta of n squared to theta of n because only one full pass, n-1 comparisons, is executed. Reduced pass length. After each outer iteration, the last I elements are in their final positions, so the inner loop can stop at n-1 minus I instead of always scanning to the end. This is already present in the standard pseudocode, but some naive implementations ignore it and keep scanning the whole array, causing unnecessary work. Combined, these optimizations give a practical bubble sort that runs fast on almost sorted inputs, while preserving the same worst-case theta of n squared bound. Selection sort works like picking the smallest or largest item from an unsorted pile and placing it at the beginning of a sorted pile, one by one. Function selection sort open parenthesis a sub 0 to n-1 close parenthesis. For I from 0 to n-2, min index equals I. For j from I plus 1 to n-1. If a sub j is less than a sub min index, min index equals j. If min index is not equal to I, swap a sub I and a sub min index. During the ith outer iteration, the inner loop finds the smallest value in the sub array a sub I to n-1 and swaps it into position I. After I passes, the first I elements are the I smallest elements in sorted order. The algorithm only swaps once per outer iteration, making it efficient in terms of write operations. Selection sort's cost can be derived directly from its 2 nested loops. Comparisons. For each outer index I, 0 to n-2, we compare the current minimum with every later element j. I plus 1 to n minus 1. Number of comparisons C of n equals the sum from I equals 0 to n minus 2 of n minus 1 minus I, which equals n minus 1 plus n minus 2 plus 1, which equals n times n minus 1 divided by 2, which is theta of n squared. This sum does not depend on the initial ordering, so best, average, and worst cases all have the same theta of n squared comparisons. The swabs. At most one swap per outer iteration when min index is not equal to I, therefore the number of swaps S of n is less than or equal to n minus 1. That is theta of n. In the best case already sorted, min index is always I, so 0 swaps occur. In the worst case, reverse sorted, we still swap exactly n minus 1 times. Time complexity. Best, average, worst case. Theta of n squared time due to the quadratic number of comparisons. Space complexity, big O of 1 extra space in place. Mathematically, the dominant term n squared divided by 2 shows the same quadratic growth as bubble sort, but the constant factor for swaps is much smaller. Invariant. After completing the outer loop for index I 0 based, the subarray A from n minus I to n minus 1, the last I positions contains the I largest elements of the original array, sorted in non-decreasing order. Proof. Initialization I equals 0. Before any pass, the last 0 elements are trivially sorted, the invariant holds. Maintenance. Assume the invariant holds for some I during the next pass, ith iteration. The inner loop compares adjacent pairs up to index n minus 2 minus I. Any element larger than its right neighbor is swapped. So the largest element among the unsorted prefix A from 0 to n minus 1 minus I moves step by step to index n minus 1 minus I. No element beyond that index is touched, so the already sorted suffix remains unchanged. Hence, after the pass, the suffix A from n minus 1 minus I to n minus 1 now contains the I plus 1 largest elements in order. Termination. When the outer loop finishes I equals n minus 1, the invariant tells us that the suffix of length n minus 1 is sorted, and the remaining single element at index 0 must be the smallest. Therefore, the whole array is sorted. Since the invariant is established initially, preserved each iteration, and yields a sorted array at termination, bubble sort is correct. Invariant. At the start of each outer iteration I0 based, the subarray a sub 0 to I minus 1 contains the I smallest elements of the original array sorted in increasing order. Initialization I equals 0. The prefix of length 0 is vacuously sorted, invariant holds. Maintenance. Assume the invariant holds for some I. The inner loop scans the unsorted part, a sub I to n minus 1 to find the smallest element min, because all elements smaller than min are already in the sorted prefix by the induction hypothesis. Min is the I plus 1 th smallest overall. Swapping min into position I extends the sorted prefix to length I plus 1 while preserving order. Termination. When I equals n minus 1, the invariant guarantees that a sub 0 to n minus 2 holds the smallest n minus 1 element sorted, and the last element is the greatest by elimination. Hence, the full array is sorted. Thus, by induction, selection sort correctly sorts the input. Stability bubble sort stable. Equal elements never cross because swaps occur only when a sub j greater than a sub j plus 1. Stability selection sort not stable by default. Swapping the minimum into position, I can move equal valued items past each other unless extra care is taken. Number of swaps bubble sort potentially O of n squared swaps in worst case. Each pass may swap many adjacent elements. Number of swaps selection sort at most n minus 1 swaps, 1 per outer iteration. Swaps are far fewer, making selection sort attractive when write cost is high, for example flash memory. Comparisons both algorithms perform theta of n squared comparisons in all cases, n times n minus 1 divided by 2 comparisons. Memory usage both use O of 1 additional space. Practical speed bubble sort often slower than selection sort on random data because of many swaps, but can be faster on nearly sorted data with the early exit optimization. Selection sort generally faster than plain bubble sort for large random arrays because fewer swaps, but still slower than more advanced algorithms like quicksort or merge sort. Typical use case bubble sort is used for teaching basic sorting, visual demonstrations, or when stability is required and the data set is tiny. Selection sort is used when right operations are expensive, or when a simple in-place sort with minimal swaps is needed. In summary, bubble sort wins on stability and on nearly sorted inputs with optimizations, while selection sort wins on minimizing swaps. Both are quadratic and therefore suited only for small n. 1. Write the pseudocode for bubble sort. Answer: provide the two-loop version shown in the first explanation, emphasizing the inner loop range 0 to n-2-i, and the swap condition if a left bracket j right bracket is greater than a left bracket j plus 1 right bracket. 2. State the worst-case time complexity of bubble sort and justify it mathematically. Answer: theta of n squared. Derivation: outer loop runs n-1 times, inner loop runs n-1-i each time, total comparison sigma I equals 0 to n-2 of n-1 - i equals n times, n-1 divided by 2 equals theta of n squared. 3. Explain how the early exit flag improves bubble sort. What is the best case complexity with this flag? Answer: the flag detects whether any swap occurred in a pass. If none, the array is already sorted and the algorithm stops. Best case becomes theta of n because only one pass, n-1 comparisons, is performed. 4. Compare the stability of bubble sort and selection sort. Answer: bubble sort is stable because it swaps only when the left element is greater than the right one. Selection sort is not stable. Swapping the found minimum with position I can move equal valued items past each other. 5. Prove the correctness of selection sort using a loop invariant. Answer: state the invariant. First I elements are the smallest and sorted, show initialization. Maintenance, finding the smallest in the unsorted part and swapping. Termination, when I equals n-1 the whole array is sorted. 6. When would you prefer selection sort over bubble sort in a real-world system? Answer: when right operations are expensive, for example sorting data on flash memory, because selection sort does at most n-1 swaps, whereas bubble sort may perform many more swaps. 7. Give an example of a real-world scenario that can be modeled by bubble sort. Answer: imagine sorting a line of people by height where each person can only compare with the person directly in front of them. By repeatedly letting taller people step forward one spot, a swap, the tallest eventually reaches the back of the line. 8. Derive the exact number of comparisons bubble sort makes on an array of size n. Answer: C of n equals sigma I equals 0 to n-2 of n-1 - i equals n-1 plus n-2 plus 1 equals n times n-1 divided by 2.